This is Ms. Black, and this is Open Campus, and we are now moving into Module 15. So just think, we just left Module 14, which was a huge module. We had graphed all those conics, the circle, the ellipse, the hyperbola, and the parabola, which were all curves. In Module 15, we only have 2 more new graphs to learn. These are also curves. So if you go to your class notes, let's discuss our 2 new curves. Okay, what we're going to graph today is an exponential function, an exponential equation. Well, if you go back to modules 10, 11, 12, we already talked about these types of equations. So what we're going to do is we're going to take those equations, exponential equations that we learned to solve, and now we're going to graph a picture of them. So we have to go back to the definition. What makes an equation exponential? And our definition is the same as it was in Module 11. An exponential equation means your exponent is the variable, and your base is a whole number other than 1. So if you look, we can write y equals b to the x. Because we're going to be graphing now, we're going to have the variable y and the variable x. So it still fits our definition. Our x is the exponent. Our b, our base, is going to be a positive whole number other than 1. And now we have the y. And we can also call that, instead of using y, we can use our function notation, f of x. So what we want to learn how to do today is, again, recognize what equation is exponential and then learn how to graph a picture of it. And because it's not linear, it's not a line, it will be a picture of a curve. So if we look here, our first question is to talk about which one of these equations are exponential. So let's go back up to the whiteboard and discuss this. Okay, guys and gals, here we go. We're going back to Module 11. I have 6 equations here. They all have equal signs. And I first want to make sure you understand the definition of being exponential. So I know everybody's written in function notation. If you don't like Fred, you can replace them with y. So I'm going to do that first. We're going to get rid of our function notation and put our variable y. The definition of an exponential function says the base must be a positive number other than 1. And the variable is in your exponent spot. So if I write y equals x squared, is that an exponential function? Is your base a positive number? No, your base is a variable. If you recall, we've already learned to graph this. X squared is what type of equation? Very good. It's quadratic. And we just learned in Module 14, quadratic equations are graphs of parabolas. So this is not exponential. Okay? We've already learned how to graph that. If we look at equation 2, y equals 2 to the x. Is that exponential? Well, is our base a positive number? Yes, it is. Our base is 2. Is our variable in the exponent spot? Yes, it is. So this is an example of what we're going to learn to graph today. Okay, let's look at equation 3. Y equals 1/2 x. So again, exponential means the base is a positive number. Is the base positive? Sure it is. It's a half. Is our variable the exponent? Sure it is. Our variable x is in the exponent spot. This is exponential. This is what we're going to learn to graph today. All right, let's go to equation D. Y equals x to the 1/2. Does it fit our definition? Is our base a positive number? No, it's not. Okay, if you remember, we're going way back to the early modules. This is an equation where the exponent is a fraction. This was called a rational exponent equation. Now, we did not learn how to graph that in this course, okay? But that does not fit our definition of being exponential. All right, let's go to E. Y equals 1 to the x. Does it fit our definition of exponential? Is our base a positive number? Well, yes, it is. But our definition says the base cannot be the number 1. Now you're going to say, why can't it be the number 1? Well, let's think about this. If this base is 1 and you put an exponent on it, for example, if you say 1 to the first, what is that? It's 1. If you say 1 squared, what is that? Well, that's still 1. If you say 1 cubed, what is that? That's still 1. So no matter what the exponent is, this base is always going to be the number 1, which means it's staying constant. And you already learned this. If you have the equation y equals 1, that's linear. What kind of line is that? Very good. That's a horizontal line because that is a linear equation. So even though we have a variable in the exponent spot, that when the base is 1, it's never going to change. This is always going to be y equals 1, which is a constant number. And we know y equals 1 makes a horizontal line. So this does not fit our definition. Okay, we go to the last one. Y equals pi to the x. Okay, the definition of exponential says the base must be a positive number. Well, somebody's going to say that's not a positive number. Remember, pi is not a variable. Pi is a symbol that represents the number 3.14 blah, blah, blah. It represents that irrational decimal. Well, is that irrational decimal positive? Yes, it is. Is the variable an exponent? Yes, it is. So this does fit our definition of exponential. So out of the 6 equations I gave you up here, I just want to make sure everybody agrees what we're going to graph today. We are going to graph exponential equations. That means the base must be a positive number, and the exponent is your variable x. Is everybody good with that so far? Great. Now, what we want to do is we actually want to draw a picture of one of these. So let me erase this, and let's go look at our notes and see what we want to graph first. All right? So our first equation we want to graph in example 2 is f of x equals 3 to the x. And if you don't like Fred function notation, that's okay. Cross it out and make it be y equals 3 to the x. So the first thing I want you to notice is this is not a circle, ellipse, hyperbola, or parabola that we just completed. There are no squareds. It is not x squared, it is not y squared. So it cannot be any of those curves. The next problem is it linear aligned? Well, you're going to look at it and say it has a y and an x. It looks like a diagonal line, but it's not, guys and gals. Remember, the equation of a diagonal line is always y equals mx plus b, which means the x is connected to a number by multiplication. Is that x connected to 3 by multiplication? No. That x is in the exponent spot. So when the x is in the exponent spot, it is not a diagonal line because it is not in this form. So we will know when we have a base that's a whole number, a base that's a positive number, and the x is in the exponent spot, this is an exponential equation. Because we said way back when in Module 11, exponential means you have a variable in the exponent spot. Now, I'm going to tell you all right now, there is no special trick to graph these equations. I know we've been working on tricks. For example, I know we learned to graph a diagonal line. You put it in slope-intercept form. I know we graphed the circle, ellipse, hyperbola, parabola. We looked at the equation and we got the numbers out. There is no trick to graphing this curve. You're not going to do anything by looking at the equation and taking the numbers out. We are going to go back to good old-fashioned way to graph. And the good old-fashioned way to graph is to plot points. And to get the points, you're going to have to set up a t-table. So there is no trick to graphing an exponential function. Your job is going to be to set up a t-table. Now you're going to say, well, what do we put in our t-table? Well, your job is to pick values for x. Substitute them in the equation to get your value for y. Remember, when you do a t-table, you can pick any values you want for x. Now, we're all in agreement. Do you want to pick decimals or fractions? Heck no, that's too much work. So normally when we do a t-table, we pick integers. positive and negative whole numbers. Because you've never graphed this type of equation before, let's pick, say, 5 values to put in our t-table. So I'm going to pick 2, 1, 0, -1, and -2. Okay? You always, when you do a t-table, want to pick some positive whole numbers, some negative whole numbers, and 0, just to make sure you covered the graph, the coordinate plane. So what we're going to do is we just pick these numbers arbitrary out of the air. That's fine. That's what's great about a t-table. You can pick anything you want. You're going to take each one of these numbers and substitute in an x in the equation like we did modules ago to get your y value. So what happens is here we get 3, y equals 3 squared. Well, we all know what 3 squared is. It's 9. So now you've made an ordered pair, 2, 9. Let's go plot that. 2, 9. Now we all know 1 point is not enough to graph any type of graph. So we'll go again. We're going to take 1, substitute it in. So we're going to write y equals 3 to the first. Well, we know 3 to the first is 3. So we need another ordered pair, 1, 3. Okay, let's go plot that. Well, 2 points is not going to be enough to graph this curve. You know this has got to be a curve because it's not a linear equation. Remember, we've already discussed linear equations are pictures of lines. A horizontal line is y equals a number. A vertical line is x equals a number. A diagonal line is y equals mx plus b. This equation is not in any of those forms. So it can't be a line because it's not linear. So it's got to be a curve. The problem is if you just plot 2 points, you're going to end up drawing a line. So we need to go and get a couple of more ordered pairs, points. Let's try again. Let's substitute in 0. So y equals 3 to the 0. And we've already discussed this. Any base to the 0 power is 1. So here's our next ordered pair, 0, 1. All right, that's looking pretty good. Let's do a couple of more just to get a feel for this curve. So now let's put in -1. So we're going to get y equals 3 to the -1. We've already discussed this semester. In algebra, we do not work with negative exponents. They make no sense. So we learned a trick. You can always change a negative exponent into a positive exponent by doing the reciprocal of the base. Who's the base here? 3. If you flip the base, do the reciprocal, you would get 1/3 to the first, which we know is 1/3. So now you've made the ordered pair point, -1, 1/3. So now we're going to plot that. Well, you're going to say, well, wait a minute, we can't plot fractions on the graph. Sure we can. Remember, these are just number lines. In between any 2 whole numbers, integers, there are fractions. So we're going to go to x is -1 and y is 1/3. 1/3 is between 0 and 1. So you just estimate. I know that I can't plot that exactly, but that's about 1/3. All right, let's plot one more point. Let's get one more ordered pair so we really get a good visual of this curve. So now I picked -2. So we're going to substitute it in our equation. We're going to get y equals 3 to the -2. Again, cannot ever work with a negative exponent in algebra. To make a negative exponent positive, you do the reciprocal, you flip the base. Does anybody remember the correct word for reciprocal? Very good. It's multiplicative inverse. Just so you know your vocab. So we're going to do the multiplicative inverse. We're going to do the reciprocal. We're going to flip that base. When you flip 3, you get 1/3. And now the exponent is a 2. Well, we all understand what that means. 1/3 squared means 1/3 times 1/3, which is 1/9. So now you've made the ordered pair, -2, 1/9. Okay, we're going to plot that. So we know x is -2. Now, here we go back to good old arithmetic. Do we understand the meaning of a fraction? I want to plot y is 1/9. Is 1/9 more than a third or less than a third? Think about it in real life. If you ate 1/9 of a pizza and a third of a pizza, who ate more? Very good. 1/9 is eating less of the pizza than eating the third. So 1/9 would be lower, so this point's got to go a little lower. So does everybody now see what's going on here? If you connect these 5 points, you make a curve. As you go to the right, these points are going to get higher and higher. We can all visually see that. We know this can't be aligned because look at the movement. Is the movement from here to here the same as the movement from here to here? No, it's not. So that's why we discussed this already. Only with lines can you talk about that movement, that slope. You can't talk about slope of a curve because from here to here you went up 6 to the right 1. From here to here you went up 2 to the right 1. You don't have the same slope, so that's why it's not a line. Now, the problem is we can see what's going on to the right. What's going to happen as we go to the left? Well, this is a third, this is a 9th. What's going to happen as we move to the left, each of these x, y values are going to get lower and lower. Because think about it. The next value we would try to substitute in is -3. And y equals -3, 3 to the -3. So if we pick -3, if we did one more point, this would be 3 to the -3, which we just said we cannot work out till we make this exponent positive. So this will really be 1/3 cubed, which is a third times a third times a third. Well, the numerator is going to stay 1, but now the denominator is going to be 3 times 3 times 3, which is 27. So what I want you to notice is, as the x values get smaller and smaller, x was -1, you got a third. X was -2, you got a 9th. X is -3 now, you got 1/27. As the x values get smaller, these fractions get smaller. But if you take 1 and divide it by 27, it's going to be a small number, but it's still going to be positive, so it's still going to be above the x-axis. And as you go to -4, we're still going to get a fraction. We're going to get 1/81, which is still going to be positive. It's going to be above the x-axis. So even though each of these points are getting lower and lower, they're getting really close to the x-axis, but they can't touch the x-axis. And you're going to say, why can't they touch the x-axis? Well, let's think about this, sweethearts. If you physically touch the x-axis, what is your point's y value? Very good. If you are sitting on the x-axis, which we know is called an x-intercept, your y value is 0. If you take a positive number and divide it by a positive number, are you ever going to get 0? No. So what I want you to understand is what's going on the left side is these points are getting lower and lower. They're getting really, really close to the x-axis, but they're not going to touch it. So when you connect the points to make this curve, you are following the x-axis from the left side, but you cannot touch it. And then it's going to start growing quickly. That's what an exponential curve looks like. Now, I know you're going to say, well, it looks like a horizontal line here, but remember, we're just doing an estimate. What I want you to notice, if you took a magnifying glass and really looked at these points, each y value is getting really, really low. This is 1/3, 1/9, 1/27. This would be 1/81. This is 1/243. This is 1/729. A positive number divided by a positive number is still going to stay positive. So these points are never going to touch that x-axis. Now this curve has a special name. It is an exponential curve, but in real life we call it the growth curve. If any of you have children and you've taken your child to the pediatrician, the doctor, what's the first thing they do with your child? Yes, they weigh them and they measure their height. And then if you open up your portfolio for your child, there is a chart. The doctor plots that information. This is how you grow. You don't grow linearly. You don't grow the same amount every year. You don't grow to make a line. You grow exponentially. That's why children have growth spurts. I have a son who's a teenager. He just went through a growth spurt. He just shot up 3 inches. He has not grown 3 inches every year of his life. He has just all of a sudden grown. So when you look at your child's growth and you plotted it on a graph, it would look like this. If any of you remember, every 10 years in the United States we fill out a census. Well, that census is to predict the population growth of America. If you plotted that information, it would look like this. So an exponential curve is important for real life. If you owned a business and you want to plot the growth of your business, you would hope it would look like this. It would keep growing. So there's a lot of practical reasons to know about an exponential curve. Okay? Now that you graphed it and you've seen it's very simple to graph, you just do a t-table, which is basically using your algebra skills. Now, just like anything else, we can ask you some questions about this picture. So my Michelangelos, my Picassos are graphing. Let's see what questions we have here. The first question, and we're going to review vocab now, is domain. I want to know the domain of this curve. Well, do you remember what that means? Domain means x values. Domain means how far the curve travels to the left, how far the curve travels to the right. Well, if you look, when I drew my curve, I put arrows. So how far to the left does this curve go? Well, this curve keeps going to the left, 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 left. The x values are getting smaller. After -10, there'd be -11, -12, -13. Because we're going to travel to the left all the way, we say we're going to -infinity. As we travel to the right, now I know it's going up, but it's not going to go straight up. Just like a parabola, it's going to open up wide. So as we travel to the right, it's going all the way to the right, which is positive infinity. And if you remember, we put parentheses when we write that in interval notation. All right, if I ask you domain, I should ask you range next. Range means low to high. How low does the curve go? How high does it go? Well, if you look, this curve, this y value is 1. This y value is a third. This is a ninth. This is 1/27. Can you actually tell me the lowest y value? No, you cannot. Each of these fraction values are getting lower and lower. But you know they will never reach what number? Very good. These points are never going to touch or sit on the x-axis. And if you're sitting on the x-axis, what's your y value? 0. All of these points are positive values. All the y values are above 0. So we would say for the range, we're starting above 0. Because we're not including 0, we put a parenthesis. So that's the lowest they're going to go. You're never going to have a y value that's negative. Your exponential curve, the y values are not going to be down here. They're not going to be negative. They're all going to be above the x-axis, which means they're all going to be above 0. So to show you're not including 0, you put the parentheses. Now, how high do the y values go? Well, we got 1, 3, 9. It keeps shooting up. It's going to go as high as it wants, which is positive infinity. Okay? Next question. What is the graph's x-intercept? Well, we've already discussed this word. X-intercept means where you touch the x-axis. Is this exponential curve ever going to touch the x-axis? No way. So we would say there is none. D, what is this curve's y-intercept? Well, we've already discussed this word. A y-intercept means where you touch the y-axis. Well, I'm looking. Here's the y-axis. Up, it's touching. So I need to name that ordered pair, that point. And that point is at 0, 1. Our last question, E. Here comes that famous word, asymptote. An asymptote is a line that the curve gets close to and never touches. Everybody look closely at your picture. What line is our curve getting close to but never going to touch? Very good. It's the x-axis. Your exponential curve should not touch the x-axis. Well, now we got to give its proper name. The x-axis is technically a horizontal line. How do you name a horizontal line? You use the letter y equals, and the y value of the x-axis is 0. So just like we've been doing, after you graph your picture, you can then answer questions about your picture. Okay, let's try one more exponential curve. So let's erase this. All right. So if you look at your notes, your next exponential graph curve is y equals 1/3 to the x. Okay, let's look at that. First of all, I expect you all to be able to look at that equation and say, well, I don't have an x squared, I don't have a y squared. It cannot be the circle, ellipse, hyperbola, parabola. That's out. I know it's not a line because it's not y equals mx plus b. This number and that variable are not connected by multiplication. Because that variable is in the exponent spot and this base is a positive number, this is an exponential equation. So I now know I'm graphing an exponential equation. There is no trick or shortcut to graph an exponential equation. I know you would like that, but we don't have one. The only way to graph an exponential equation is to do a fancy t-table. Now, when you do a t-table on your own, you could pick as many x values as you like. I just did the first exponential curve with 5 x values. Do you really think we need 5, or can we lower that? Yes, we can. The minimum number of points we need to plot to make this curve obviously is not 1, because 1 doesn't help us. It can't be 2 points because that would make a line. So it's got to be 3. So you need at least a minimum of 3 points to make an exponential curve. You could pick any numbers you want. I'm going to be safe. I'm going to pick a positive number, 1. I'm going to pick always 0, and then I'm going to pick a negative. Okay, so you can pick anything you want. Those are the 3 I always pick. If I have to set up my own t-table of values to graph any equation, I pick 1, -1, and 0 to be safe. So now it's time to substitute. Let's take 1 and substitute it in. This would be 1/3 to the first, which means 1/3. So I am plotting the point 1/3. So I'll go to x is 1 and y is 1/3, which is somewhere in the middle. It's higher than 0, but it's less than 1. Okay, let's take our next x value. Put 0 in here. So this is 1/3 to the 0, which we know any base to the 0 is 1. So now I've made the ordered pair 0, 1. 0, 1. Okay? Now I'm going to plug in, substitute in -1. So I'm going to write 1/3 to the -1. Ooh, but wait a minute. We discussed this all semester. You cannot work with a negative exponent. Anytime you're given a negative exponent in algebra, you make it positive. How do you make this exponent positive? You do the reciprocal of your base, the multiplicative inverse of your base. If you flip 1/3, you get 3 over 1, which is 3, and 3 to the first is now 3. So our last ordered pair is -1, 3. -1, 3. It is obvious that's got to be a curve and not a line, because look at the movement. The movement here is down 2 to the right 1. The movement here is down just a little bit to the right 1. It's not the same movement, so it can't be a line. That's why the concept of slope we only mention with lines. So when you connect this, you're making a curve. Now look, we got to connect the 3 points. So there we go, we're connecting them. So obviously, as we move to the left, this is going up. As we move to the right, this is going down. But remember, if it's exponential, it is not going to touch the x-axis. So that should be your picture of your exponential curve. Okay? That's obviously not growth. Because if you look at it from the left to the right, your finger is going down. It's decreasing. So it's not a growth curve. The opposite of that in real life is a decay curve. Now, why would that be important? Well, if you were born in the 60s, there were no Pampers or Huggies or Loves. You wore cloth diapers. But in the early 70s, Pampers just came out. And when Pampers came out, all the moms of the country were all excited. The environmentalists of our country were very upset because Pampers, Huggies, and Loves, those diapers are made of plastic. And back in the early 70s, plastic was not biodegradable, which meant if you put a diaper that was a Pamper or Huggies or Loves in the landfill, it sat there forever. The plastic did not decay, come apart. So back in the early 70s, a lot of environmentalists were using this kind of graph to show, hey, if you put a Pamper in a landfill, it's going to be there forever and ever. Okay? If you're an archaeologist, you would be looking at this because you're talking about the decaying of a fossil. So there is a lot of practical reasons for a decay curve in science. Okay? Just so you all know, there is a reason to learn about it. Our job as a mathematician is to appreciate every equation makes a unique graph. And then once we make our graph, we can answer our questions. So let's go over our vocabulary one more time. Domain means what? X values. How far does the graph travel to the left? How far does the graph travel to the right? So if I look, even though I'm going up as I go to the left, I'm opening up. And I keep going to the left all the way. All the X values are going to get smaller and smaller as we move to the left, so we're going to negative infinity. As we move to the right, it's going to keep going to the right. All the X values are going to get bigger and bigger. We're going to positive infinity. If you're a memorizing person that likes to memorize facts, that's the fact. The domain of an exponential curve, whether it's a growth curve going up or a decay curve going down, is always going to go from negative infinity to positive infinity. It's going to travel in both directions. Just like our friend the parabola, who went to the left and right all the way, just like our diagonal line goes to the left and the right all the way. All three of those graphs have a domain from negative infinity to positive infinity. The range, though, is different. The range is the y values. How low can this curve go? Well, this curve is never going to go down here. So never is its y values going to be negative. The y values are getting smaller and smaller, but they're never going to be 0 because an exponential curve is not going to touch the x-axis. And if you do not touch the x-axis, your y value cannot be 0. So we would say the lowest value is something above 0. That's why we put a parentheses. We're not saying 0 is the lowest value. It's something above it. The highest value of our y's, well, this is always going to shoot up. So that's going to be positive infinity. Again, if you want to memorize that, that's great. Memorize those facts. X-intercept. Does our exponential curve touch the x-axis? No way. An exponential curve does not have an x-intercept. Y-intercept. Does my exponential curve touch the y-axis? Sure it does. Right here, because that's a point, you need to name it as a point with an x value and a y value. This point is located at 0, 1. Does this curve have an asymptote? There's our funny new little word. Asymptote means a line that's technically invisible that the curve approaches but doesn't touch. Your exponential curve is always going to get very, very close to the x-axis but never touch it. To write the equation of the x-axis correctly, it's a horizontal line. We learned in the previous modules, horizontal lines are always written y equals. And what is the y value on the x-axis? It is 0. So in this module, we learned about a new graph that's related to an equation we solved a long time ago. Exponential curves can either grow or decay. All right, I'll see you in the next module.